Welcome back. Lecture 17 today. We have some things to wrap up from yesterday's lesson, but not very many things. Then we'll forge ahead about kind of interrelationships of graphs and their derivatives. If you start with the original graph, we did a little bit of this yesterday. Can you come up with a graph of the derivative? And what we did not do yesterday is if you start with the derivative, can you come up with what the original graph might look like? There will be a couple things that we'll need to know in addition to just simply going back and forth there. We finished with the idea yesterday of if a function is differentiable, then it is what? Continuous. So if we know for a fact that the derivative exists at a point, that means it's differentiable. It has a derivative at that point. Then we know there must have been a point there on the original function, or the derivative would not have existed to begin with. So if it's differentiable, then it's continuous. We decided yesterday that the converse being formed by interchanging the hypothesis and conclusion, so basically the if and then statements. If it's continuous, then it's differentiable. We decided what? Not true. So I finished with the idea of a contrapositive, reasoning by contraposition, or contrapositive is probably the way you saw it, probably the first time in a high school geometry class. It's where you saw that the first time. How do you take an original statement and form its contrapositive? Anybody remember that? So if we switch if and then statements, that's converse. What do you have to do to form the contrapositive? Okay, kind of. If you just switch signs, that would be, if you negated the hypothesis and negated the conclusion, that would be called the inverse. Now, if you do both of those together, you do the converse switching, and you do the inverse negating, the converse of the inverse, or the inverse of the converse, then that becomes the contrapositive. So you've got to switch hypothesis and conclusion and negate both of them. How would that read?
It's not continuous.
Yeah. It's not continuous.
What do you think about that?
True.
That's true. And in fact, whenever an original statement is true, automatically its contrapositive will be true. So if you switch hypothesis and conclusion and negate them, it's a true statement. Converse and inverse also work that way together. Does it bring back bad memories from high school geometry? I hope not.
Yeah,
but the contrapositive is true. If we know for a fact it's not continuous, then it clearly is not differentiable at that point or throughout its domain. A couple of other things. They address higher order derivatives at the end of that section. Be nice if I knew how to spell it too. Yeah, this is math. It doesn't matter, right? No, it does matter. Higher order derivatives. So we've seen already second derivative. We've seen a use of second derivative. We started with a distance, height, or position function. We took the derivative and got a velocity, took its derivative and got acceleration. And I guess we could go even further than that and take its derivative and get something, some term called the jerk of x or whatever t in this case. But this then would be s prime. This, because it's the derivative of the derivative, would be s double prime. So we've seen second derivative already. There are such things as higher order derivatives. I think Kent mentioned the fact that these are used primarily in things like Taylor and Maclaurin series, which you'll get to in Calc 2. But the notation is what the book addresses here. So we've seen f of x. We know its first derivative. The instantaneous rate of change is f prime of x. The derivative of that would be the second derivative, and you can find third derivative. Now, after a while, the little tick marks up there get a little bit redundant. So if you see a superscripted number, like a superscripted 4 in parentheses, that would be the fourth derivative. Or the seventh derivative, you're not going to make 7 little tick marks. So we'll do that like that. Other notation for derivative that you'll see in this book, we have started this. dy over dx, that's the derivative of y with respect to x. It's the same thing as f prime of x. That would be the notation then for second derivatives, kind of the second derivative of y with respect to x both times. It looks like dx squared, but it just means you've taken the derivative with respect to x twice. Third derivative of y with respect to x all 3 times, and so on. So that's another notation that these authors use. Really, both of those are pretty much interchangeable. And we'll begin to use those as we go into the next section, which is where we are right now. So we want to be able to, when we're done with this section, by the way, if you have the old edition, the previous edition of this book, we're in the 3rd edition. If you have the 2nd edition, either in this class or somebody on cable TV or on DVD, this section is actually 2.10 in the previous edition, and 2.9 from the previous edition has actually been deleted or kind of subsumed in another Chapter 3 section. But this is the last section in Chapter 2 in Edition 3. So it's what does f say about f prime, or you can change that around too before we're done. We want to know what does f prime say about f. So we want to be able to take ideas, and we're also going to throw this in a little bit. We might, it's in the book, but I don't know that we're quite ready for it yet, but it'll be the first time we encounter it. We'll see it a lot later. What does f double prime? So if we know some things about the second derivative, what does that say about the function? But basically, we want to go back and forth. If we know facts about the function, can we graph the derivative? If we know facts about the derivative, can we come up and graph the original function? And a lot of it is pictures, but some of it is just what does that picture, how do we interpret that picture as far as increasing and positive and those kinds of things. And we'll incorporate today terminology that has come up, I think, maybe on one occasion in this class, concavity, concave up and concave down. Came up one day in this class, and we really didn't address it, but we're going to begin to address it today. So let's say that we have some things we know about f prime of x. If we know that some of this is a little redundant from yesterday, we're just going to kind of make a list. If we know that the derivative is 0, so we know that is true about the derivative. What does that say about the original function? It's a what?
It's a constant.
It's a regular number.
Okay, some of those things are true. So not a constant, but I think you want a
Critical
specific.
value.
It's a specific point.
Right. And what about that point?
Look, it turns flat.
It's flat. Okay. At that point, the function is flat. Now, it might be the idea of, Katie said the idea of a max or min that comes into play, and we'll address that. It may be, in fact, a relative max. It might be a relative min, but it might, in fact, be neither of those, and that all three of those situations can happen. Let's just go ahead and make a, let's say the graph looks like this. There, the derivative is 0. And on this particular picture, because it was increasing into there, then flat, and then decreasing out of there, that creates what? A relative max. So we might have a relative max. It's decreasing into there and increasing out of there. Again, the derivative is 0. That would be a relative min. Now, the idea or the difference between a relative max and an absolute max, somebody want to tackle that?
The absolute max is the definite height of the graph.
Okay, the absolute highest point on the graph, right, would be an absolute max, or sometimes called a global max. I don't use that term very much. So I'll use absolute max and relative max. So what's a relative max?
In that area.
In that area, in that, sometimes called a local max, which might actually be even a better term. So in that locality, it's the highest point. But there might be higher points elsewhere on the graph. But in that area, it's the highest or the lowest point. So it's given that little prefix, relative. Now let's say we have a horizontal tangent line right here. Let's say it's increasing into here, getting flat. So that's kind of what happens, right? It starts to begin to get flat, and then in fact it is flat, and then it increases out of here, so it leaves here fairly flat and does that. It's still possible to have a place where the first derivative is 0. It is instantaneously flat at this point, but it was not a high point, nor was it a low point. There is a subtle change there. Does anybody want to tackle that?
Inflection.
Okay, it is potentially a point of inflection because this piece of the graph is concave down, and this part of the graph is concave up. But it is not a relative max. It is not a relative min. And we could have that same thing happen in this fashion, where it's decreasing and it gets flat. At that point, it's instantaneously flat, and it continues to decrease. Again, not a relative max, not a relative min. Question?
What about something that kind of plateaus off?
Well, that would never actually have a specific place where the derivative is 0. So if it does, like, eventually get flat, like, let's say, a square root curve, there is not a specific point where the derivative is 0. In all four of these graphs, there is a specific place where the derivative is 0. So that'll make that different from what you asked. So if the derivative is 0, we know we've got a flat place. We don't know the nature of that flat place. That'll have to come in from the rest of the information that's given to us. So since I'm starting anew here, I'll just redo my columns. Let's suppose that the derivative is less than 0. Derivative is negative. What's that mean about the...
The original was a
Slope
function.
is
Decreasing.
Well, not the slope is decreasing, but the curve itself is decreasing, right? This means that the slopes are negative. And that will come back up, though, Jonathan, that idea of the slopes decreasing and the slopes increasing. So we want to separate that because that actually means something else. This, because the slopes are negative, this means that the original function is decreasing. Kind of touched on that, right, yesterday? I don't know that specifically was written down. But if you think about it a second, the only way the slopes could be negatively sloped, I mean, the curve could look like that. These slopes are all negative, right? The curve could look like this, right? Those slopes are all negative. Slope there is negative. Slope there is negative, right? So it's falling from left to right. So if the slopes are negative, if the derivative is less than 0, the curve itself is decreasing there. So if the slopes are positive, what's that say about the function itself? What's the function doing in that area?
Increasing.
It's increasing. So since we're drawing pictures here, let's continue the picture idea. There's a curve. Not only are the slopes positive, but the curve is doing what from left to right?
Increasing.
Increasing. So this is, I guess I should label my graphs. And it could look like increasing, but yet increasing in a different fashion. These slopes are also positive. So if the slopes of the tangent lines are positive, that curve is on its way up from left to right. So what are we missing? We had the derivative equals 0, derivative is negative, derivative is positive. What are we leaving out?
It's not as-
Undefined. So if, in fact, the derivative is undefined, what does that say about the function?
Should go straight vertical.
Yes. So if you think about lines that have undefined slope, so the slopes are undefined. What types of lines have undefined slope? Vertical lines. So you use this terminology. I don't think I used this yesterday, but I'll say steep. As it approaches there, it gets steeper and steeper. At that instant, it's as steep as it could possibly get because it's basically vertical. The curve at that instant is basically straight up and down. Now, there are lots of ways that you can kind of get to this steep picture. And I don't think we've looked at this particular type of picture. Let me draw the tangent line first. So it's a vertical tangent line. Now, could the graph, if there is a point there, so we want to actually include that dot. Let's say that the curve did something like this, and it gets steeper and steeper and steeper, and at that instant, the derivative is undefined because the slope of the tangent line is undefined. It's a vertical tangent line, and it leaves here very steep, and it does something like that. That is possible. That is possible to have a vertical tangent line, and the curve is completely defined there. It's just that the derivative doesn't exist there. Chandler.
Doesn't that also have a horizontal
Well,
slope?
Down here.
Right at that point? No, at that point.
No, it's vertical. If you think about coming in from the left and from the right, so as you approach that vertical, these tangent lines, as you come in from both directions, are getting steeper and steeper and steeper as you go.
Okay.
And at that point, the tangent line is, in fact, vertical. So it doesn't mean that you've got a vertical asymptote. Now, that is true when you have a vertical asymptote. If you think about what that means, here's the picture. What's happening to the tangent lines as you get closer and closer to that dotted line? Aren't they getting steeper and steeper, right? More and more vertical. So this tangent line compared to this one this one compared to this one. As you approach that vertical asymptote, they're getting steeper and steeper and steeper. So I know the terms aren't very mathematical and not very exacting sounding, flat and steep, but if it helps you kind of make that picture, I know it helps me make that picture. The derivative is undefined. I know that as I get close to there, it's getting steeper, and at that very instant, if the point exists, it's as steep as it can get, which is vertical. Okay, we have addressed local max, relative max. Let me put those terms down. I'll probably use the term relative max more than local max, but both are used in the book. These basically are for that general vicinity, for that locality. It's the highest point in that region. What's going to lead to a local or relative max? Well, let's suppose that the curve is decreasing, which means its derivative is what? Negative. Then the derivative is 0. Then the derivative would have to be positive. Is that correct? Yeah. So decreasing into there, flat, and then increasing out of there. Is that what I want? Not what I want, is it?
No.
Something that goes from increasing to decreasing.
Yes, there we go. So I want to change this. That wasn't sounding right to me. We want to start with it increasing. Then it's flat. And then it's decreasing, right? So if the derivative is positive, then the derivative is 0, then the derivative is negative, then we've got this thing called a local or relative max. A local or relative min again, both terms will be used in this book. So to create that, we'd have to have what? We want a low point. So we want it to decrease into there, which is what I tried to do a minute ago, which wasn't working. Then we want it to be flat. And then we want it to, what? Increase out of there. So this means the original function is going to be decreasing. Then it's flat. Then it's increasing. And if, when you look at the totality of the whole picture, if that is in fact the highest point on the graph, then it could be absolute max. The lowest point on the graph, then it could be an absolute min. Now, does it have to be, are these the only places where we could have a relative min and a relative max? What else could happen? We've already seen.
Sine and cosine.
Well, could that be a relative max?
Yeah.
That could be it is, in fact, not only a relative max. If this is the whole graph, this is an absolute max, isn't it? What's the deal there? It's undefined, right? So it is possible that the derivative could be undefined, right? And that could generate a place where we have a high point or a low point. So we'll call those kind of points when we search for them. They're not called this yet in the book, but we'll call those critical points, where the derivative is 0 and where the derivative is undefined. All right, so this is our first look at second derivative stuff. You're not necessarily responsible for all of it just because we talk about it for the first time today, but it is the first time it's in the book. So eventually we'll build a body of knowledge about second derivative. So let's look at a couple pictures first, and then we'll start to build this body of knowledge about second derivative, and what does it say about the original function. So let's say the curve has this kind of shape, and I'm not necessarily talking about the increasing, but what's going on with the slopes. So let's take some slopes. Slope of the tangent line right here, right here, and right here. What's happening as we move from left to right? What's happening to the slopes?
It's coming more positive.
They're all positive, but
Getting closer.
it's flattening out, isn't it? So this, maybe the slope here is 3. The slope here is 1/2. The slope here is 1/5. So they're all positive, but as we go from left to right, what's happening? They're decreasing. The slopes are decreasing. So not the curve itself, but the slopes are decreasing. Now, if the slopes are decreasing, this is the only kind of shape it could have, is this shape, if the slopes are decreasing. So that shape is concave down. And if the slopes are decreasing, that means that the second derivative is negative. So we're still increasing as far as the basic shape of the graph, but the rate at which it's increasing is slowing as you go from left to right. It's not getting steeper, it's getting flatter as you go. Well, when that happens, we end up with a curve that has this kind of shape, concave down. That means the rate of change of the rates of change are negative. Okay? So the rates of change of the rates of change would be the derivative of the derivative, so second derivative is negative. So let's say the curve has this basic shape. So we've got a slope here, slope of the tangent right here. So maybe the slope here is -4. The slope here might be -1. The slope here might be -1/5. As we go from left to right, what's happening to the slopes? The slopes are increasing. They're getting less negative. Is that true? And if you don't like this part of the diagram, let's get to the rest of this over here. Here the slope maybe is +1. Here the slope is +4. So the slopes are clearly increasing. Now, if the slopes are increasing as you go from left to right, it has to have this kind of shape. All we have to do is give that kind of shape a name. What is it? Concave up. So what causes that? The rates of change of the rates of change are in fact positive. Now the one thing about concave up is it's got a nice little abbreviation, which is C up, which it kind of looks like that. Okay, it kind of looks like a cup, right? So you've probably seen that. It's helpful. I wish we had the same thing over here. This is cup-shaped, concave up. Unfortunately, we don't have something here unless you try to make it work like a frown or something. Concave down is a frown. I don't know. That's pushing it. But this is nice. Got a nice little abbreviation. Cup-shaped, concave up. So that, I hope, makes really good sense from the pictures. Slopes getting smaller, concave down. Slopes getting larger, concave up. That's the only way it could, in fact, happen. Now, this isn't probably quite as clear, especially the first time you see it. And that is what happens when the second derivative is 0 or the second derivative fails to exist. Okay, possible points of, right, possible inflection points. With the emphasis on the possible. They may or may not be. They're candidates. We do have to check and see that they are, in fact, points of inflection. Possible points. Now, what will determine if it is, in fact, a point of inflection? What has to happen there? Okay, if they will be points of inflection, so if the function changes concavity there. If it changes, it is a point of inflection. If it doesn't change, then it is not. And let's go back to this picture we had earlier where this thing was increasing, getting steeper, includes that point, leaves here fairly steep, and does that. Is this point a point of inflection? Well, just look a little bit left and a little bit right and see what you see. This part looks like it's what? Concave up. This part looks like it's concave down. So did it actually change concavity there? Yes, that's a point of inflection. The graph, though, might look like this. Here's a possible point of inflection. Is it a point of inflection?
No.
This is concave up. This is concave up.
It, like a cusp or a corner.
Yeah, right. That would be a corner. So clearly the first derivative would not exist here, and we'll probably find out that the second derivative does not exist as well. But if this is a potential point of inflection, it would not be a point of inflection because it did not change concavity there. So this one is yes, it is a point of inflection. This one is no, not a point of inflection.
So there can be a point of inflection whether it's equal to 0 or it doesn't exist?
Yes. These are the two candidates that create possible points of inflection. Either the second derivative is 0, and if you think about it, 0, if something is 0, it could be negative on one side and then positive on the other, and then it goes through that value of 0. Well, if it's negative, second derivative is negative, and then it's positive with 0 in the middle, it did change concavity. Also, something could not exist, and that's another way it could go from negative to positive or positive to negative. So these are the possible ways it could change concavity. So I don't think really, maybe that term has been mentioned once to this point in the course, but I don't think we've dealt with it as far as what it really meant. It's a point, there's a subtle change. It's not necessarily from increasing to decreasing or vice versa. Here the whole graph is increasing, but there's a subtle change in the way it's increasing. Here it's increasing very sharply and steeply. Here the rate of increase is slowing down. So that point is recognized as a point of inflection. We've got to have our little dose of trig today, so let's start with sine of x. Let's not. Let's start with cosine of x. Change my mind here. We could go both directions, but I want to go this direction first. So if we had a picture, try to come up with a sketch, but make it as accurate as possible, of the cosine of x. Where would that start? Cosine of 0 is
One.
positive 1. Where is it at pi over 2?
0.
At pi?
-1.
3 pi over 2, 0, and then we're back where we started at 2 pi. So let's say there's our picture of one period, one cycle of the cosine. Let's say, and I call this the f of x. Let me go back and change that and call it the f prime. So this is really the derivative of something. We don't know what it's the derivative of. Some of you do. Okay, try to forget that fact right now, and let's validate it in our own mind. So this is really the f prime. Can we start with the f prime and go back to the original f?
Yes.
Well, let's see if we can. So here the derivative, I would start with these and kind of recommend that to you, that you start with these. Here the derivative is 0. If the derivative is 0 here and 0 here, what does that say about the original function? It's flat. So we know that this graph is flat at pi over 2 and flat at, everybody okay with that? Derivative is 0, means that this curve is flat. Derivative is 0, means that this curve is flat. I'm not going to start plotting points yet. Okay, here the derivative is positive. Aren't all these values positive? Right? So if the derivative is positive, what's this curve doing? From 0 to pi over 2. So again, the derivative is positive. What is the original function doing? Increasing. Is that correct? Everybody okay with that? Here the derivative is negative from pi over 2 all the way through pi, all the way to 3 pi over 2. Right? Negative? So we're on the derivative curve. Derivative is negative. So if the derivative is negative, what's the original function supposed to be doing? Decreasing. And then back to 3 pi over 2. After we get past 3 pi over 2, the derivative is what? Positive?
Yes.
So from 3 pi over 2 to 2 pi, the curve should be increasing again. Can you, in your wonderful depth and breadth of knowledge of trigonometry, can you think of a function that's flat at pi over 2, flat again at 3 pi over 2. It increases in the first quadrant, basically, from 0 to pi over 2, right? It decreases in the second and third from pi over 2 to 3 pi over 2, and then it increases again in the so-called fourth quadrant.
Tangent.
Well, why would we throw out the tangent?
Because it's not continuous.
Because it's not continuous, and the tangent is going to fail to exist at pi over 2. Did our derivative ever fail to exist? No, it was positive, 0, negative, down to -1, back to 0. It always existed. So although there might be some similarities, that one discrepancy is going to throw it out as a candidate. Several of you said sine. Okay? Isn't all this information true about the sine function?
Yep.
Now, here's a little bit of the difficulty in coming up with f, if you know f prime, is you don't really know where to start. So we'd have to know a specific starting point. So as long as I say we're going to start here at 0, the y value is also 0, I think we can finish the graph from there. So what's it have to do in the first area? It's got to increase, and then at pi over 2, it's got to be flat. Okay? So there's the flat part. What has to happen now from pi over 2 all the way to 3 pi over 2? It's got to decrease. That decreases. And then at 3 pi over 2, it's flat again. Sine seems to be working, right? And then the last piece, it's got to increase. So it seems like, now what did we just do? This is the first time in this course we just took an antiderivative. We started with the derivative, and we came back to the original function. So we took an antiderivative. So we took the shape of the derivative, came up with a graph that was the original function. So if f of x is sine of x, and the derivative is cosine, there we have our first. Now, we can check this, by the way, and I think we should. If we started the other way, if we started with the sine and we wanted to come up with the derivative, we would graph the cosine. So it is, in fact, true, and we'll validate this with algebra, not just graphs, that the derivative of the sine is, in fact, the cosine. Now, somebody had their hand up, but let's do one more thing before we leave this page, and then we'll answer that question, try to answer the question. If you started with the sine graph and you tried to work your way back here, we need to be able to go both directions, so let's do that here. The slope of the tangent at pi over 2 is 0. Is that point right there?
Yeah.
Is that correct? Yeah. So the fact that the slope of the tangent is 0, that gives us this point. The fact that the slope of the tangent is 0, doesn't that give us that point? This is increasing, which says this ought to be what? Positive. This is decreasing for quite a while here, pi over 2 to pi, and then again from pi to 3 pi over 2, which says this graph ought to be negative. So that's matching up. That's probably a little bit easier, isn't it? To go from this one to this one. We've already got the slope of the tangent is 0 here, which gives us that point. And this is increasing, which says that this is positive. So we need to be able to go both directions. Somebody had your hand up. Yes, Jonathan.
Is the point on the sine graph at pi, is that a point of inflection?
On the sine graph at pi. What do you think?
Yeah.
That point right there?
Yeah.
What about the graph left of here? In that general vicinity, that's concave down. Is that correct?
Yeah.
Okay. And right of here, that's concave up. So that appears as if it's going to be a point of inflection. Now, we don't technically have the derivative of sine and cosine, so we could take higher order derivatives. But let's see if this makes sense. If we start with sine and we take its derivative, we get cosine. What if we wanted to take a second derivative? Then we would have to take the derivative of the cosine. Any guesses? Wouldn't that be nice if it were sine again?
Yeah.
Not quite so lucky. It's the negative of the sine. So we will be able to find second derivative, and we will be able to set it equal to 0 and validate things like that. But we're not quite there yet. All right. Let's see which direction probably is a little tougher. Let's say that this is the derivative. Okay. I wanted to do one thing before I left that, and and we do have time for that. I'm going to come back to this, but back to the sine and cosine graph, I want to do one more thing. When we had the cosine graph, and it looked roughly like that, we came up with a sine graph that was right where we wanted it to be. Could we have come up with a sine graph that was up here?
Yes.
That would have still been true. So that's why when I said I'm going to choose that point to be right down here, we've got to know where to start, or we've got to have a specific point on this curve when we're going to anti-differentiate. So all the same stuff is true here. The slope of the tangent is 0 at pi over 2. So you've got to be careful where you start it. That's why you can have parallel curves. Get a better one than that. Whether you start the sine right here or you start it down here, the slopes are the same at certain locations. So you do have to have an additional piece of information. You've got to know kind of where to put it, some point to put it through. And it might be this point. You force it to go through that point. That tells you it's not this graph, but rather it's this graph. Blair.
This is kind of far off, but is that where the plus C comes from in integrals?
Yes. Yeah.
That leaves the area where you don't know.
That's
where it
exactly
is.
right. So this could be shifted. Think about what a plus C does. It shifts something up or something down, right? So we know what kind of curve we want. We just don't know exactly where to put it in the plane. So there can be all kind of parallel curves. You can have parabolas that are parallel, in a sense. Parallel meaning they have the same shape, but they're moved. That's the same curve as this. It's just shifted down something, C units. So if you've done some calculus and you've dealt with that plus C before, here is the plus C, a picture of the plus C, and what it means is we can't be sure until we know a specific point. We lock into a specific constant. All right, let's get this and finish up with it. If we had this derivative graph, could we come up with the original function? Yeah, this was a little tricky. The fact that we called this, actually Kent did this, so it's his fault. He called this the derivative, and we're going to come up with the function. Let's add this to it. Okay, actually this is good, Kent. Thanks a lot. There, the slope, now I'm not on the original graph, I'm on the derivative. The slope on the derivative graph is 0. What is that? Isn't that the derivative on the derivative graph?
Yeah.
Second derivative.
So there, the second derivative is 0. Is that correct?
Yes.
And here, the second derivative is 0?
Yeah.
Yes.
Because we're on the derivative graph, and we're finding derivatives on the derivative graph. There, the second derivative is 0. So all three of those places are what? Potential points of inflection when we get down here. First point I would actually use is this one. The derivative graph is 0 there. What does that say is happening right here, whatever that value is?
Well,
Zero.
On the derivative graph, we're
Vertical
0.
slope is right.
This graph should be what there?
Vertical.
Flat. Right? Derivative at A is 0. So if we go back from the derivative to the original function, this graph at x equals A, we are flat, right? 0 here means flat here. All these are positive. All of these are positive. So that means the entire graph is doing what? It's increasing in all those areas. Now, its rate of increase is going to change. It's increasing, and then its rate of increase, these are less positive, right? Then they become more positive, then they become less positive. Well, more positive, less positive, what's that mean down here? I'm going to say it goes through here, by the way. I'm going to pick a point. I'm going to say it goes through there. Tell me what it does. it increases,
And it flattened out.
and then
Increases.
its rate of increase kind of changes, right? Didn't we say there's a potential point of inflection in there?
Yeah.
Okay, so maybe it's this way, and then it's this way. It's still going to increase all the way, right? Until we get to A, and what happens at A?
Decreases.
It's going to be positive, increasing, 0, flat, negative, what? Decreasing. So at A, we're running out of time here. Don't we have at A flat point? And then after that, it decreases. Now, do we have some potential points of inflection along the way? Yes, we do. And that's from here, here, and here. But it's increasing all the way till we get to where the derivative is 0, flat place, after A, then we know it's negative, which means it decreases. So that was a little bit tricky. Thankfully, and I know you're about as frustrated probably as I am, that we don't have any shortcuts for derivative yet. Those will start tomorrow, so we don't have to go all the way back to the definition of derivative. We can do some shortcuts from this time forward. See you tomorrow.